topic assessment of fatigue strength of thick-walled nodular cast iron with Dross. It's a specific topic, and first of all I have to acknowledge all my co-authors from Fraunhofer LBF and also from Fraunhofer Institute for Non-Destructive Testing and the colleagues from BMB. The topic and the motivation why we are looking at this topic is related to nodular cast iron components with really high wall thicknesses and with really high weights up to 320 tons for one each single component. So we have a lot of application for larger components, especially in wind energy for the hub, mainframe, planet gear, carrier and so on. And if we have large wall thicknesses, then the likelihood that material imperfections will occur is much higher. And in this topic, we are looking at Dross as a quite specific material defect that we have to take into account. And Dross is quite specific, and if we do not know how to treat this material defect, and if we do not know how how the Dross influences the lifetime of the component, then the Dross is worked off, or the component is rejected. And if we talk about 50, 60 or 70 tons for one component, this is really tough work. Dross, for all that are not familiar with this topic, is more or less a connection between oxygen, sulfur, magnesia and silicon that is created during the solidification of these cast components. We have a reduced ductility, a reduced fatigue strength, and at the moment there's no classification. So there are classifications for the evaluation of shrinkages based on the ACM, but there is none for Dross so far. And the problem is the material of this Dross is lighter than the melt. During the solidification, the Dross swims up to the top of the component and is then located on the upper part of the casting, and then might create there a high reduction of the fatigue strength. And the challenges for us are, or especially for the foundries, to avoid Dross, which is quite costly. And we have the challenge to detect Dross and to, then at the end to make a lifetime assessment of Dross. And here on the right side you see a picture of magnetic particle inspection, and all those stringers and circles that you see here, this is Dross in the component. So the aim for us is to get a lifetime estimation based on non-destructive testing. So we heard so far a bit from other colleagues dealing with this non-destructive testing methods. And at the end we need a determination of the local fatigue strength for these larger components and an assessment concept to take Dross into account if it's present in the component. The material we were looking at in this project is typical ferritic GJS 415. It's widely used, especially in Europe, for a normal mechanical industrial application, and especially also in wind energy for more or less all of the cast components in a wind energy turbine. We created Dross specifically in the foundries by pouring 2 blocks during pouring process, and we got melt here in the pouring system, and by dropping the weight and the melt about 50 millimeters into the form, there we create a lot of turbulence, and then we catch up a lot of oxygen from the air, and then we create a lot of Dross. And here you see a picture of the block having about 40-50 millimeters of Dross layer on the upper part here in the component. We did a lot of non-destructive testing. I cannot talk about everything in detail. We did mechanized ultrasonic testing, sampling phase array and so on, and also magnetic particle inspection. You already saw a picture. You can do this either fluorescent or in black and white. And as already introduced, all these stringers, circles you see here in both pictures, that is Dross on the surface. And we use this information then to remove fatigue specimens and tensile specimens in different areas of those cast blocks that seem to be interesting for us. There's no real classification at the moment for Dross, but we try to pick up specific parts and specific, let me say, forms of the Dross that we could identify by applying magnetic particle inspection. Those specimens that we manufactured afterwards were again non-destructively investigated. We did X-ray computer tomography. You see here a picture of a specimen with a highly stressed volume affected by Dross. You see a picture of a magnetic particle inspection and also a so-called Baumann-Abdruck identifying the sulfur content in the Dross. And you see that we have different methods to detect the Dross, and we have different ways of showing what the Dross shows in different manners. Here it's volume, here you see the stringers, and here you see the sulfur content. So different ways to get to a point of knowing where the Dross is. We did then fatigue testing on several rolling test rigs under strain control test for alternating loading. You see here the test rig on the right hand side. We have mounted here 2 extensometers to get also information about the different stiffnesses on the component, on the specimen. And on the left side, the specimen itself with a thickness of about 8 millimeters. After having tested, we will have a look now on the stress strain diagram. We see here in the blue line the quasi-static material behavior, and we have for the sound condition here the green line. So we have a cyclic hardening effect, but that's not the topic of this speech. We will have to focus here on the Dross results. You see we have a large scatter, and we also see that we have here different stiffnesses, so the Young's modulus changes because of the different Dross content inside the specimen. And if we have a closer look on the results, and we then took both results from the 2 extensometers we mounted on each specimen, and here we have some results for the mean values for those stiffness measurements. We call it virtual Young's modulus because it's not really a Young's modulus, but that's not the main point. We see that we have a reduction of the stiffness of down to 8 gigapascal, and for the sound condition we're talking about 165, 170, 175 gigapascal, a bit depending on the microstructure of nodular cast iron. But we know from further results with the shrinkages that we can get a connection to the density in the test volume, and so also in this project we remove the test volume where we measured already the density, the stiffness, determine the density, and if we make a regression between both values, so the density measured in the test volume and the stiffness measured in the test volume, we get a fairly good correlation between both values. We already did this for shrinkages as well, which worked as well. And so in this case, if you have this correlation, you can model your component a bit more precisely. So if you have a component in the foundry where you have information from ultrasonic testing about the position of the Dross and the stiffness or the density in this case, then you can make a remodeling of your component and see if there is a stress relief on some points, or if you have a change in the stress situation, which definitely will occur, and to make a more precise fatigue assessment. But we also wanted to see if there is a connection then to the fatigue life. So we have here the strain life diagram. Again, here in green, the sound condition as a reference, and we have here a lot of specimens that failed more or less initially. So there was so much Dross inside, they more or less failed initially. And all those specimens, when we determined here the stiffness, we came to the result that they are more or less lower than 50 gigapascal. And so we think then there might be so many cracks present, this might be then a topic for colleagues from fracture mechanics. But we will focus now on those results here, the specimens that obtained a certain lifetime. And for our assessment concept, we now try to identify a fatigue notch factor that we call KFD. KF is well known, and we add here a D for the Dross, so an attenuation factor that helps us to, let me say, identify, based on the density measurement and based on the stiffness, a certain attenuation coming from a reference curve. Here in the SN diagram, we have a reference SN curve, which is basically the SN curve we saw already in the strain life diagram just by recalculating it for the elastic parts. And In green, we have here the different fatigue results with Dross, and we calculated in the first step just for probability of the survival of 50% here, a KFD value for all the different specimens. And if you compare this to the stiffness of this virtual Young's modulus, you see that there is a good correlation. So if the virtual Young's modulus gets lower, then we have also higher attenuation or a higher fatigue notch factor at the end. So if we have then, just as a short explanation, the assessment procedure that we follow, that we propose, is that if you have information from the geometry, the local positioning, and the density from the material defect, then you can get to virtual Young's modulus, you can get to local fatigue notch factor, and then make calculate an SN curve based on those information, helping you to make an assessment of the lifetime for each specific part of the component. And then you get rid of all classifications that you have in Dross, for shrinkages, for instance, and you have a calculative and repeatable measure because you have an ultrasonic test device which gives you always the same result, even if you do the measurement 100 times. So, to sum up my presentation, Dross is one of the most problematic material defects that we have in the foundry surroundings, and we try to use now information from ultrasonic testing, so from NDT, with the density information and so on to get to local fatigue assessment concept. In the next steps, we have to do some further results to identify the influence of mean loads. We only tested so far alternating loading. We have also a topic of multi-action loading, especially in wind energy. It's a big deal. And we have to also prove the concept and for other nodular cast iron materials. Last but not least, an acknowledgement for the Federal Ministry of Economic Affairs and Energy that funded the project with the name Unverdrossen. And thank you so much for your attention. And I'm open for questions. Thank you.